see about this? Because Daniel sort of teased about it this morning already. Now I'm going to talk about. Yeah, hi, I'm Ellie, and I'm going to talk about any material accretion and flyby encounters. So that's going to be mostly FU Ori related. And if you want to see more or are interested, I'm going to put some of my results when they come out on my website that's listed at the bottom. All right, so to start with, and I hope this works now, just going to give an overview. Some people have seen it here, some people see it for the first time. Yep, that was pretty much. Yeah, I'm done with my talk now. I'm going to sit down again. That was pretty much everything we found out in data, which was mainly about FU Ori. So just to briefly go over it, FU Ori is a star that's pretty much up here in the constellation of Orion, and it's then suddenly in 1936 became really bright, and you could suddenly see it just from observations through binoculars, and no one knows why that happened. So recent observations initially were thought to be just a single star, and then just became bright, and that was it. 2004, it was discovered that it's actually a binary, and these are more recent observations from ALMA, which show that we have actually two sources, one in the south and one in the north. And the interesting thing is that you can already see in brighter, but you can see more from this one, and it's actually FU Orionis, which if you look at both of them as a smaller star, that's right, but it's actually the one that's an outburst. So we have here two stars, so we have the Loma star actually being an outburst. Oh, I forgot to turn this on again. Which is actually the interesting question that we had. So why is the Loma star in outburst? And just briefly, because I don't know, beside Nicholas who knows about flybys, we have done flyby scenarios where we have a star that's at the center of a disk, and then we have a secondary that's passing by, depending on the direction of the disk in the middle, which is rotates and which the flyby flies. We have, if we look at this one here, a retrograde one going opposite to the disk rotation, or if we would have it in the other direction, we would have a prograde one. And then depending on what the plane of the flyby happens, it's an inclination going around the disk. All of our simulations that we've done were actually disk penetrating flybys. So we had different distances at periastron, the shortest distance between both stars, that we varied to look at what happened. So initial results for that were on the right. The left one is the actual image from FU Ori, where you can just see how it changed brightness. And this is actually the results that we had in our simulations. So this is the mass accretion rate of the primary star. We can just see it just had a small bump, and then it just continued. While the secondary star actually didn't have any material to accrete prior to the encounter. And then once it passed through the disk, there was a sudden jump in accretion. And then since then, it dropped down again. So unfortunately, it didn't stay at the same level as what we've seen in FU Ori, which stayed bright ever since it became bright. But I mean, it's still brighter than what we saw before. So even though this has dropped down again, it's still in outbursts. But the problem was that we couldn't, exactly reproduce this. Although we must also say this is on a scale of a few years, like 50, where we have over 100 years in our time scale. But even if we look at a shorter one, it wouldn't match this. But I mean, it could fit with some other FU Orionis type stars that have been discovered. So we were looking at how could we possibly increase this. And as Daniel mentioned this morning already, so we're doing phantom with MC-FOSS. So we actually have live radiative transfer calculations in our simulations with updated temperature throughout the simulations. And so we've now changed it to, initially we had one central star and with the disk surrounding it and another star passing by. And then we change it that we now have two stars, both of them have a disk around them. And so we have here, we set our primary to 1.2 solar masses and a secondary to 0.6 solar mass, roughly based on what the masses in FU Ori are. And then we created a disk around the primary with 50 AU and the secondary with 17 AU. The primary disk mass was at 0.02 solar mass and the secondary at 0.007. And this is roughly the flyby trajectory. So we changed rotations of either disk and therefore also the inclination, where we change it in such a way that in all our simulations, this always came from the bottom left and flew past like this. So we could just compare them visually easier. So we varied the inclination angle between 45 and 135 in order to make it prograde or retrograde. So yeah, the periastron distance for these simulations mainly stayed at 20 AU because that's what we found in our FU Ori simulations initially had a rise time of roughly what was seen in FU Ori. So we just kept that and mainly changed the disk rotation. So here's an example where we're showing the initial simulation from FU Ori where we just said there is a secondary, you can't really see it because it's hidden right now, but it just has a disk around the primary. And then we had 4 other simulations where we changed the disk rotations. So prograde or retrograde, as mentioned before, is if this flies in the same direction as the disk is rotating, it's prograde, and otherwise it's retrograde. But then we also, because we now have 2 disks, they can rotate in different directions. And so I'm like showing this with my hands. So we're seeing this from the front, so we don't really see that they're like in different like depths, but they're actually coming towards each other like this. But we looked at what the rotations are relative to each other. So here we have both of them rotating in the same direction relative to each other. And then here we have them rotating in opposite directions. So all 4 of these simulations compared now are running. So we have on the left the retrograde ones. Here we have the prograde ones. These are the ones where they rotate in the same directions, and these were the opposite signs. We can see in depending on retrograde or prograde that we have different tails and structures forming. But what is even more interesting is, in a moment, I don't want to stand in front of this, is we can see that in these ones, the secondary actually has more denser material surrounding it, while in these ones, we can actually see a lot of dense material forming on the primary as well as on the secondary. And this is actually something that we can also see more clearly when we're looking at the temperature, because as we said, we have live radiative transfer, so we can actually see the temperature is changing throughout the simulation. So we have here all 4 simulations listed at the top. They're going down in rows. And then we have taken the snapshots that are surrounding periastron, where we get the highest temperatures. And we can see here that depending on the scenario that we're using, can you see my mouse? Yeah, good. We can actually see temperatures spiking around different places around the stars, or also in the disk. So in the past, in the previous one, we saw the temperature spiking and the mass accretion rate changing in around the primary, secondary, which we continue seeing for the prograde cases. So we have the secondary going around like here and the primary going around like there. So these are the secondaries here that are in outburst. Well, actually in the retrograde cases, we can see that the primary as well experience an outburst, which even looks, well, it's confusing a bit, but it's like it appears as if it could even be brighter. One thing to notice, as you can see at the top, these are normalized temperatures. We exceeding actually 1500 Kelvin. So those are temperatures where we would see dust melting, and that's what we're working on next, where we can see if such a scenario in the past could actually in the solar system have led through the creation of chondrules that we can find in meteorites, because we have these high temperatures and we're currently trying to see if the cooling rates are going to be fast enough. But these changes here are also observed in the mass accretion rates. So the top row shows the mass accretion rates of the primary, the middle of the secondary, with the right side each showing the corresponding luminosity. And at the bottom, we show the total luminosity because, I mean, FU Ori, when it was first observed, there's 2 stars, but you didn't know that. So you just had the total of both of them, just like that's the luminosity we're observing. And so we can see that this was what we had previously, and it dropped down quite low again. And if we have a secondary disk prior to that, we can actually see that while it still drops down, our mass accretion rate is sustained at a higher level than what we saw if we don't have a secondary disk. It's still not ideal. We're still not seeing what we see in FU Ori, so there's still more to be found there, but we're getting a bit closer at least. And what we found with this one was actually because we're looking at the material that we have there, and we looked at when that, that outburst happens. So what we saw here, these outbursts, they happen at slightly different times. You can see the dotted line is when periastron happens. And some of them are just starting just before that, and some of them as periastron occurs. So we're showing here a snapshot from every single simulation when we had the highest accretion. And we can see in all of them that there is actually a lot of misaligned material around these stars that actually leads to, especially in these ones where we had the high accretion on the primary, you can see that there's a lot of the material that is misaligned in relation to what it was the initial plane of the disk. And so we actually found that the outbursts are driven if we have sustained and sustained if we have a lot of misaligned material that then leads to a rapid change in the total angular momentum. And we actually further looked at where does the material come from that either star is accreting. And so we looked at the, so these are all the simulations. We looked at the mass that they each accreted, each star. And then we looked at what the percentage of the mass that they accreted is that is actually coming from the opposite stellar disk. So where we had the primary, the secondary flying by, and then a bunch of material that's getting accreted is actually from the secondary disk. And we found that large amounts of what they're actually accreting is from the opposite disk. So it's actually alien material that's not from the host disk. And that the primary actually only goes into outbursts of at least really 33% or more is from the opposite disk. Although we must say that if we're looking at this, these masses that are accreted here are comparably small to the other one. So even though most of this was from the opposite disk and there was a spike to be seen, it was still of a smaller scale than what we saw for the other cases. But overall, we just found that it's important that we have a bunch of material coming into the star to feed the accretion. And so to summarize, well, we found out that if the disk penetrating stellar flyby can lead to a fast rise time and also make the low mass star going into the outburst. And then if we have 2 disks prior to the encounter, we can sustain the outburst for a longer time. If there is a large fraction of alien material, that the outburst gets sustained a bit more. And also that depending on the scenario we have, because with FU Ori, we know the low mass stars and outbursts, but there's other FU Orionis stars where we don't know yet if there's 2 stars in there or not. And if there is the primary or the secondary, that's an outburst. But with the scenarios that we have, we can at least say that if we have both stars and outbursts or just a secondary, we can either say it's like a retrograde or prograde trajectory. Thank you.
Questions for Ellie? Yes.
Am I correct that for calculating the accretion rate, you're using the particles that just come into the sink radius? So that sort of assumes you're like infinitely cooling, like you're cooling the material infinitely fast and then you're just immediately accreting. But do you think you can sustain the luminosity if the accretion is mediated by some other like mechanism like angular momentum transport timescales or cooling timescales?
What was the first time scale?
Angular momentum transport in the disk.
Yeah, we think that if we would have a continuous material that could infall, that we could be able to sustain the outburst for longer.
More questions for Ellie? Follow-up for Ellie? Can you elaborate on you saying that it's when you have this misaligned material that causes the accretion?
Yes.
What's special about the misaligned material, the misaligned stuff that makes it accrete more or faster?
So it's like a cancellation of angular momentum that just leads to. I don't know how to explain that right now.
That's okay. Cool. Yeah. Thanks. I think everybody's keen to go for coffee.
Yes.
So with that, thank you very much to Ellie and the other speakers for this session. And we come back at 11:40.